So welcome everyone again for this week's lectures. This time, we've been doing in the past few lectures a lot of technical things, about quantum field theory, about black hole backgrounds, and so on. In fact, the course is of course titled the Black Hole Information Paradox, and this week we are going to arrive at our first paradox. The idea I thought today was to try and go through Hawking's original paper in some detail and just try and formulate the paradox as Hawking formulated. Before I go to that paradox, I just wanted to say a few things about the derivation of Hawking radiation that we did last time, and just say a few words about its significance, and then, because that's something that we'll come to again and again, and then we'll go on to the paradox. I hope you remember that last time we derived this formula, which told us that the temperature of a black hole was proportional to its surface gravity. This formula, of course, is it's important, and the way we derived it was by working out the occupancy of some modes of quantum fields. But in fact, this formula has another implication. One of the importance of this formula that we'll find is that it's, the fact that black holes radiate is relevant for the information paradox. But in fact, this formula also had another implication. It didn't just lead to a paradox. It also kind of solidified another piece of intuition that people had. And that was that even before Hawking derived this formula, people had learned just by analyzing the classical physics of black holes, that there were some laws that are sometimes called the laws of black hole thermodynamics that happen to look like this. Okay? So this K is the same surface gravity that you see. And this is the angular velocity of the horizon, which one can define precisely. This is the angular momentum. This is the charge. And this is the potential at the horizon. Okay. This K is the same K that appears here. And this A is the area. So this is something that one can just derive just by analyzing classical processes around black holes. So the kinds of processes one looks at to derive this is you take a black hole and then you throw in some particles, and then the mass changes a little bit. If the particle has charge, the charge of the black hole changes. If the particle or the stuff you throw in has angular momentum, the angular momentum changes, and you can write down a relation between how much the mass changed and how much these other quantities changed. And this is something that people had established well before, before this derivation of Hawking radiation. And there was a second thing that one can also derive independently of Hawking radiation, and that's the fact that we say black holes are black, but in fact, as those of you who've taken courses in general relativity know, in fact, it is possible sometimes to extract energy from black holes using something called the Penrose process. But classically, it's never possible to reduce the area of a black hole. Okay? So in any classical process, you can sometimes reduce the mass. It's not necessary that the dm, which appears on the left-hand side here, that this dm is negative. This dm could be positive or negative. But this dA that appears here, this always has a certain fixed sign, and this dA is always positive, and that's something that people had found. And if you think about it, this mass, after all, is the same as you can think of it as the internal energy of the black hole. And this looks a lot like the laws of thermodynamics, right? And in thermodynamics as well, you would have exactly the same terms having to do with the angular momentum of a body or having to do with the electric charge. And there's also a second law of thermodynamics, which tells us that the entropy of a system, of an isolated system, always increases. Now, before Hawking's derivation, if you just looked at these two parts, so these are BH, these are laws of black holes, and these are laws of thermodynamics, you might have thought that this is an example of what Feynman calls, if you for those of us who anyone who's read the Feynman lectures knows that Feynman keeps saying the same equations have the same solutions. And it indeed does happen many times in physics that you end up with the same equations again and again. I mean, you take a mass on a spring, and that obeys the same equations as an LC circuit. That doesn't actually mean that a mass on a spring is an LC circuit, but they both have a certain universal feature of oscillating in a particular way, and therefore they have the same equations, and if you know how to solve one, you can solve the other, but they're distinct physical quantities. But one of the significance of deriving the fact that black holes really had a temperature was that these analogies, this analogy between the laws of black holes and the laws of thermodynamics, is not just some formal analogy. It's not just an example of the same equations having the same solutions, but really black holes do behave like thermodynamic objects. And the reason they obey some laws of black hole thermodynamics is because these are the laws of thermodynamics. Okay? And so one of the important implications of this derivation of the temperature is that it forces us, it tells us that black holes not only have an analogy with the laws of thermodynamics, but they really do obey laws of thermodynamics because they are thermodynamic objects. And this also tells us, by the way, that the entropy of the black hole is A over 4. Okay. So you can see this by comparing this equation with this equation. So if you compare this equation with this equation, you will see that if you equate the temperature with K over 2 pi, with the surface gravity over 2 pi, then the way to make the first law of thermodynamics work is to make A over 4 the entropy. Okay, and so the fact that you are able to derive a certain specific coefficient for what the temperature is also tells you that there's a specific coefficient that relates the area of the black hole to its entropy, and that's 1 over 4. Okay. Okay. I should say that in these assignments, which some of you might have looked at, there's often a question of working out what the numbers are. It's important that black holes actually have a lot of entropy. If you look at black holes of the kind that you see in the sky, they have a lot of entropy compared to everyday objects. In particular, for the sun, if you work out how much S is, it's of the order of 10 to the 76. And that's just comes from just working out the area of the sun. There, by the way, units here, which I haven't put in, which have to do with the Planck length. But this is the area in Planck units. And if you work out what the area of the sun is in Planck units, you find that it's something like 10 to the 76. Okay? So black holes have a lot of entropy. So black holes are objects which have very large S. And we are going to actually return to this many times. And one of the things I'd like you to keep in mind as we go through these arguments about the information paradox, one of the things that we should never forget is that black holes are thermodynamic objects with a large entropy. Okay? So they're not they're not just some objects which have a few microstates, but they're objects which have a very large entropy, and that will be relevant for us in the information paradox. There is, of course, an entirely orthogonal direction of research which has been a very fruitful direction which one could take, which is to work out properties of this entropy and try and count the microstates of the black hole. We won't do so much of that in this course, but the fact that black holes have an entropy and the fact that that entropy is very large is important, and it's an important implication of Hawking's derivation of the Hawking temperature. Okay. So that's just something I wanted to say about the implications of the derivation that we completed last week. I now want to go on to the first paradox, which is Hawking's original formulation of the information paradox. Okay, so I thought that the way we would do this is actually by trying to go through Hawking's original paper. So I have Hawking's original paper here. We're not going to read all of it, but the idea I had was that maybe we could try and read some snippets of it and try and understand what Hawking's main point was. Okay? So Hawking's the information paradox was first outlined by Hawking in this paper. I mean, there are other papers in it, but this is an important paper, one of the original papers where the information paradox was outlined. And so the paper is titled "The Breakdown of Predictability in Gravitational Collapse." Okay? And that's really a statement of the paradox. It's the fact that if you start with some initial state, and what Hawking is going to try and argue is that in the end, the final state that you end up with is a mixed state because you end up losing some information, and this the fact that you lost some information Hawking pointed out had to do with the causal structure of the space-time, and we'll go through the arguments that Hawking had. Okay? I just want to say a few things as we go through this paper. Well, one of the things I wanted to say was that there are many versions of the information paradox. There are many arguments that people have developed as in the information paradox, and I sometimes feel, at least as somebody who thinks about these issues, that the phrase Hawking's paradox is often misused in a sense, in that many people say Hawking's paradox, or many experts sometimes might say Hawking's paradox, when actually they're referring to their own paradox about black hole evaporation, when they're referring to an argument that doesn't appear anywhere in this paper. And so I think it's important to try and delineate the arguments, and the plan for today's lecture and for tomorrow's lecture as well is to try and follow carefully the original arguments that Hawking made. Okay? I also want to say that, in fact, I will try and argue to you that this original paradox, when it's framed in the way as it was framed by Hawking, is something that it is not so hard to find a resolution to, and we will discuss possible errors in the argument that is outlined in this paper, and also possible resolutions to the paradox that is outlined in this paper. I'm not going to try and discuss those errors today. I think today we'll just try and go through the argument as honestly as we can, as faithfully as we can to the original paper, and then we'll discuss tomorrow what the possible shortcomings in this argument might be. But the fact that we can find shortcomings in this argument doesn't end this course. There are many aspects of the information paradox that we will keep returning to, and there are many, in some sense, more formidable paradoxes that one can outline, which we will move on to. But the plan for today's lecture, tomorrow's lecture, and maybe one half a lecture after that is to look at this original argument and try and point out some issues with that. Okay, good. So let's try and jump in and try and see what Hawking's point was. So the first point that Hawking made, I wanted to strongly suggest, I would very strongly recommend that everyone read this paper. If you're interested in the information paradox, this is a paper that you must read, because this is the original paper on the subject, in a sense. So you should, I would strongly suggest that you read this paper. But I'm not going to read the whole paper. I have in advance marked some passages, and what I'm going to do is I'm going to read those passages, and I'll try and explain what those points were. And so we'll have to come up with a concise version of the argument, but you should in your own time try and read this paper and try and understand it. And there are these tutorials we are having, and so you should feel free to have more discussions about this paper there. Okay. So the first point that Hawking made, Hawking starts by talking about singularities and so on. But for us, the first relevant point is the fact that Hawking had already argued by the time this paper was written, in the previous paper. So he pointed out, as the discovery by this author, which is his own discovery, that black holes create and emit particles at a steady rate with the thermal spectrum, which is what we were just discussing. And because this radiation carries away energy, the black hole must eventually lose mass and eventually must disappear. Okay? So this is something that's pretty simple to understand. Let me just give you a few more details of the fact that the black hole must disappear, because Hawking doesn't give those details here, but there's some simple details one can work out about the rate at which the black hole disappears. And so the details are just as follows. You see, we worked out some rate at which the black hole loses mass, and what we worked out actually was the occupancy of some modes which were out modes, right? But you could try and integrate that the flux at null infinity over all of these modes, and you could ask, what is the rate of change of the mass of the black hole with time? Okay? And you will find that this rate is, remember, we are always in d+1 dimensions, space-time dimensions, and you will find that this rate, this is a constant. This constant actually, to work out in detail what this constant is, you'll have to work out the gray body factors and sum them. But for simplicity, you could think of this like the Stefan Boltzmann constant. Okay, so there's some constant that tells you that's in front of the rate of change of mass, and then there is the area, and this is the temperature that we have worked out. Okay, and this is the space-time dimension. So this almost follows from dimensional analysis, right? It follows almost from dimensional analysis that if you have a body which has a temperature T, there are some modes it's emitting, and you just try and sum over all of those modes, and you will find that the rate at which the black hole emits energy, or the rate at which this body emits energy, is proportional to the temperature to the power d+1, because the body has some area. You have the area that appears, and then there's some constant that appears. And on the whole, this is if you just look at black bodies in the lab, this is just the Stefan Boltzmann law. It's the fact that dm by dt is minus sigma t to the power 4. But this works in higher dimensions as well. Now you can convert all of these quantities. The black holes we are looking at and that we have analyzed, and that we will continue to analyze for the rest of this course, are very simple black holes, because they are specified by a single parameter, which is the radius of the black hole. And so these black holes are very simple, and this mass of this black hole is very simply related to the area of the horizon, just by this. Okay. Remember, I wrote down at some point the formula for the mass of the horizon of a black hole, and you can check in flat space that the mass and the horizon are related in this way. I should have said, by the way, that just to avoid any confusion, previously we discussed both ADS black holes and flat space black holes. In the lecture today, we are talking about flat space black holes. That's the context in which Hawking, of course, formulated the paradox. And remember, that's the context in which there was a flux. In the case of ADS, we didn't even have a flux at infinity. Okay? So the mass is just some part of the horizon radius. The temperature is the surface gravity, but you can work out that the temperature is just 1 over the horizon radius, up to some constants which you can work out. And the area, just by dimensional analysis, is RH to the power d minus 1, right? And if you now put in, if you just put in these proportionalities into the equation we have on top, you will find that the rate of change of the horizon is just minus 1 to the RH to the power d minus 1. Okay? And the way that comes about is, you have an RH to the d minus 2 on the left, you have an RH to a d minus 1 on the right, and then you have a 1 by RH to the d plus 1 that comes from the temperature. And then there are various constants. The constants that appear here are not the C constant, but we don't care about the constants. In the assignment, actually, you are asked to work out these constants more carefully. But the rate of change of the horizon is just proportional to 1 over RH. Okay. Now, the interesting part of this is that, and the fact that so you have some radiation being emitted. And when this radiation gets emitted, the mass of the black hole reduces, and therefore the radius of the black hole reduces. And you can see immediately from this formula that in a time that is proportional to RH to the power d, remember the space-time dimension is d plus 1, so in 4 dimensions this is RH cubed, okay, and which also happens to be proportional to the area of the black hole divided by the temperature. Okay. RH to the power d, as you can see from these proportionalities on the left hand side, is also proportional to the ratio of the area and the temperature. Okay. We have that RH goes to 0. Okay. And what this tells us is that if you take a black hole and you have a black hole in an isolated universe where there is no other process that's competing with Hawking radiation and trying to increase the mass of the black hole, in a time that's just proportional to the initial radius to the power d, the black hole evaporates away entirely. Let me point out another feature of this evaporation. It is the fact that the flux increases as RH decreases. The rate of change of RH increases, but in fact the flux also increases, because you can see A is proportional to the RH to a d minus 1, whereas T to the d plus 1 is 1 by RH to a d plus 1, and therefore just the rate of change of mass also just increases as RH becomes smaller. So what this means, and the reason this is happening, is because the black hole is becoming hotter and hotter. Okay? So the black hole starts its life radiating at a certain rate. As it becomes smaller and smaller, the rate at which it is radiating energy becomes larger and larger and larger. And in the end, towards RH goes to 0, there's an explosion and there's some flash, and the black hole ends its life. Okay, so this is just an elaboration of what Hawking said. It's just some trivial computation that tells you that the black hole radiates and it loses energy. and in a time which is proportional to the initial horizon radius to the power d, the black hole evaporates. The rate at which it evaporates is faster and faster as the black hole becomes smaller and smaller. So if you have a very big black hole, the very big black hole is not actually a very hot black hole. The bigger the black hole, the cooler it is. But as the black hole becomes smaller and smaller, the radiation becomes more and more violent. And in the end, the black hole just completely evaporates away. So this is just a fact which follows almost, we are forced to this fact from the fact that we derived Hawking radiation. Okay, so this was the first point that Hawking made. Okay, good. So far so good. So far, we haven't said so much. We just pointed out that, if you derive radiation, then you must also, you must have the fact that the black hole will eventually entirely radiate away. Okay. Now, the next thing that Hawking points out is that if you look, so Hawking points out that the causal structure. So, is there a question?
Yeah. The black body radiation of Stefan Boltzmann law for black hole is valid also for per black hole.
Yeah. So yeah, you can work out in some. So there's in the assignment question you asked to work out these gray body factors. So you can try and work out the gray body factors in detail, and you will find that you will have black hole evaporation, which you can work out this constant as well. It's not hard to work this constant out.
Okay, so it's a general phenomenon.
It's a general phenomenon.
Okay. But how do we define the area for a rotating black hole?
How do you define the area? One can define the area of the horizon for rotating black hole. So what could I suggest that maybe you could ask this in the tutorial where this can be discussed?
Yeah, it isn't a function of theta. That's what I was worried about.
The area is an integrated quantity, so it's not a function of theta.
It's a codimension. Okay, yeah, I'm sorry.
Okay, thank you. Sorry, someone asked, is the metric of an evaporating black hole just so no one has actually ever worked out the metric. So the question is the metric of an evaporating black hole just a Schwarzschild metric? So no one has actually worked out the entire metric of an evaporating black hole. The point is that the Hawking radiation is happening over some time scale, and the back reaction is presumed to be small. Okay. So one assumes that the geometry, this process is like a quasi-static process. So you have some evaporation. After some time, the mass is reduced, and then you have to now use the new temperature of the black hole and then compute how things work. But the derivation that I gave is a heuristic derivation. There's no detail. I mean, there are attempts, but there's no. I don't think there's really a good rigorous attempt to try and work out what the entire space-time geometry of an evaporating black hole is. The intuition behind what I said was the fact that you have a quasi-static process where you have radiation. So after some time, you expect that the mass decreases and the temperature increases, and therefore the rate of radiation changes. But you're right that it would be nice to have a complete metric of the entire process, including back reaction. And as I said, there's some attempts in the literature to do this, but it's not really been done very carefully. It's a hard problem to do it completely carefully.
Okay. One question. So does that mean that we can't be very sure about the disappearance of the black hole? Because the mass loss power law maybe not.
So you expect that this physics that you're deriving, the fact that actually, if you look at Hawking's paper, I added some details to Hawking's paper. Let me just go back. Hawking only said that, the fact that the black holes are creating particles and are radiating means that eventually they must lose mass and they must become smaller. We will discuss in the end whether this radiation, whether this could stop when the black hole becomes like close to Planck scale. When the black hole becomes very small, maybe it doesn't evaporate, and this physics that we're deriving doesn't work. But the fact, while the black hole is much larger than the Planck scale, we expect that the physics we have derived should hold, and the black hole should become smaller and smaller. And so the idea, as Hawking, Hawking didn't write down all the equations I did, and in a sense that's good because one doesn't have to answer all of these questions. All one has to say is that if one is an observer far away, then you expect that you have this radiation coming out. So whatever is inside must be shrinking. And it's true that this shrinking could stop very close to the Planck scale. We'll have a little bit more to say about that towards the end of this lecture. But most of the black hole will clearly evaporate away if you start with a black hole that's much larger than the Planck scale. So what happens at the very end of black hole evaporation is not, the eventually disappear in this line is not very important. It's the fact that it must eventually become smaller and smaller till it becomes, till a point where maybe quantum gravity effects become important. But as we'll discuss at the end of this lecture, that's not important for the paradox.
Thanks.
Okay.
Actually, can I ask? I have two very quick questions.
Yeah.
The first one is the value of the entropy that you gave at the beginning.
Yes.
Is it the entropy of the sun if it were a black hole,
yes.
right?
The entropy of a black hole with the mass of the sun.
Yes, perfect. Okay, and the second question is that proportionality with respect to the horizon radius for the mass, temperature, and area, etc. Do they apply to not just to Schwarzschild black holes, but also Kerr, for example?
No, there would be other parameters that would appear there, and so you would have to be careful about other parameters. In the case of the Schwarzschild black hole, it's simplest. In the case of other black holes, there are other parameters, and so you have to be more careful about that. For instance, you could jack up the angular momentum so high that the temperature just goes to zero, so you could have an extremal black hole. And so the fact that the temperature is 1 over the horizon radius, the formulas I gave are all valid for a Schwarzschild black hole, and that's already enough for us to frame the paradox.
Okay, so we focus on Schwarzschild black holes and not Kerr.
For simplicity, you could work out the same thing for Kerr black holes. If you have a Kerr black hole which is not extremal, it would still evaporate. And so you could work out the same kind of, you could set up the same kinds of paradoxes for Kerr black holes. But the qualitative features of the information paradox are already very clear with the Schwarzschild black hole. And so, one could look at black holes with other charges, and for sometimes they are of interest. In these entropy computations, one almost always looks at black holes which have other charges as well. But for this simple discussion, we can just focus on the Schwarzschild black hole.
Thank you.
Yeah, thank you. Okay.
I have one question. Why isn't the shrinking at odds with the second law?
Yeah, you see, the second law is a classical relation. So in the end, the entropy of the Hawking radiation that's emitted is more. There's actually a generalized second law. If you have a lot of radiation being emitted, what you really need to ask is, what is the entropy of the initial black hole plus the entropy of the Hawking radiation? So there is a second law that is valid. So Page, for instance, has done some computations. The entropy of the Hawking radiation is more when the black hole eventually evaporates and you just have Hawking radiation, that radiation has more entropy than the initial entropy of the black hole. So it's true that there is a classical second law which tells you that the area of the horizon always decreases. In the Hawking process, indeed, the area of the horizon is decreasing. There is still a second law of thermodynamics, which is now a generalized second law, which is you have to take the area of the horizon divided by 4, add to it the entropy of the Hawking radiation, and that quantity always, still increases. But the area of the black hole itself could decrease because that's compensated by the entropy of the Hawking radiation.
Okay.
Yeah. Okay. Are there other questions? Okay. Thank you. Great. Yeah, great. Yeah. So Hawking's second point was.
I had a question. Is the area itself an asymptotic observable?
The area itself, I don't think is necessarily a good asymptotic way to measure the area.
So everything else in the thermodynamic relation was an asymptotically defined quantity, right?
Well, there were other quantities we defined in the first law of thermodynamics, which were not which had to do with the angular velocity of the horizon, which had to do with the potential of the horizon, and so on. So there were other quantities that went into the black hole. When you talk about black holes as thermodynamic objects, you have to have a sense in being able to isolate the black hole from other objects, right? Which is the discussion we just had about, the fact that there's some generalized entropy of the entire system. But at least classically, you would like to say, here's a black hole and here's the radiation, and you can think of them as separate subsystems and add the entropies. So I don't know of any good way to define the area, purely asymptotically, where you just define the area as an asymptotic observable. The area is the area of a black hole. You could have two different black holes with two different areas, which you define by, looking at the black holes locally. Maybe there's a good way. I don't know. But it's kind of, again, the spirit is that black hole is a system with a given area, a given entropy, a given temperature. And it's a thermodynamic system. So you don't try and define the area asymptotically. Okay. Okay. So I think, okay.
I have a question. Can I ask?
Yeah.
When you say the entropy of the radiation, you mean this is entanglement entropy of the radiation?
No, just the thermodynamic entropy of the radiation. When you define the entropy of the radiation, it's the way you define the entropy of a gas. So there's a well-defined S maximization. Whenever you talk about the thermodynamic entropy, it's a coarse grain entropy. Oops. sorry, my Zoom went off. Whenever you define the thermodynamic entropy, it's a coarse grain entropy. Let me just answer the question, and then I can say, when you define thermodynamic entropy, it's a coarse grain entropy. So what you do is you say, you make some observations in the Hawking radiation of some correlators, and then you ask what is the density matrix with the largest entropy that's consistent with these observations, and that's the thermodynamic entropy. So I really mean the thermodynamic entropy of the radiation.
Thanks.
Yes, I should probably go back to the excellent. Okay, great. Okay, so we should probably go back to Hawking's paper. So Hawking's first point was that when one looks at, even classically, right, when one looks at the black hole geometry, you see that if you have information about a Scri plus, that's not enough to retrodict the information on Scri minus. Okay? So this is simply the point that if you have, the point that Hawking is making here in this paragraph here, is the fact that the causal structure of the black hole is different, and that's that. Let me just explain what that point is. That point is the fact that if you take a black hole, then, as we discussed many times, you have the horizon, you have Scri plus, you have Scri minus, right? But we need data on the horizon and Scri plus, right, to determine what the initial state was. So we need data on H union Scri plus to determine what was happening at I minus. And that's already different classically from what the causal structure of Minkowski spacetime, where if you know what's happening at Scri plus, you can retrodict what's happening at Scri minus. But if you know, so if you want to get this, if you, in the case of the black hole, you see that even classically, to get data at Scri minus, if you wanted to retrodict from Scri plus what was happening at Scri minus, you would have a problem. You would also need data about what happened at the horizon. So this is, in fact, this is just classical intuition, but this is something that, this classical intuition kind of runs throughout the argument in the paper. And in fact, the point of the argument in the paper is just to make this classical intuition precise. It's the fact that, if you, whatever falls into the horizon is kind of lost to the observer far away. And that's true classically, and the point of the rest of the paper is kind of to try and make that precise. And because whatever falls into the horizon is lost to the observer far away, to the asymptotic observer far away, if you just have some observers, who started up with some data on Scri minus, and then later try and, collect everything that's coming out from the black hole at Scri plus, then they would have lost the information that went into the horizon. So that's the first point, which at this level has just been made classically, but now we'll try and make the same argument more precisely quantum mechanically. Okay, so that's the next thing that Hawking tries to do. So he says, this is the point about the classical structure being different. Yeah, excellent. So the next point Hawking makes is that this is also true quantum mechanically if you go through carefully the calculation that we did previously. So what Hawking is doing here is Hawking is just computing the density matrix that one would compute at Scri plus using observations of Hawking radiation. So in particular, what Hawking tries to do is Hawking tries to compute the occupancy of some modes, which you see here, some occupancy of some modes at Scri plus, and that's an occupancy that we already saw and computed. And let me just try and explain how that occupancy works. Okay, so remember that we expanded in the first few lectures the field in terms of these modes, right, which we call A omega L, and we multiplied with some functions F out, and then we had some other modes which we multiplied with some functions F in, and these were multiplied with some spherical harmonics, and there was a Hermitian conjugate. And our derivation of Hawking radiation was in the end a derivation of what the occupancy of these A omega L modes was. And what we said was we actually did something which was, I mean, maybe slightly simpler technically than what Hawking did. What we said was that, we defined some small A omega Ls, which were smeared versions of this big A omega L. So these big A omega L are some delta function normalized operators. And then we computed, what this small A omega L, what the occupancy of this small A omega L was. And we found that A omega L dagger was just 1 by 1 minus e to the minus beta omega. And the fact that A omega L times A omega L dagger has this form tells you that there must also be a non-zero occupancy for capital A omega L dagger. We are computing these A omega Ls are slightly, you can think of as coarse-grained versions of the A omega Ls, of the capital A omega Ls. But the fact that they have a non-zero occupancy tells you that there must also be a non-zero occupancy for the big A omega Ls. And remember that this function f out that multiplies the A omega Ls, as you go to Scri plus, it had some form that looked like this, which we already emphasized. Okay. And then there's some other gray body factor that we didn't write down, but that we already discussed a few times. And the fact that we had some flux that was emerging at infinity just had to do with the fact that if you computed the stress tensor at null infinity, and you have to multiply it with the appropriate power of r, then this is non-zero, because you have these modes that multiply this kind of an outgoing wave, this kind of an outgoing wave, and the modes that multiply this kind of an outgoing wave are occupied, and therefore if you compute the stress tensor at infinity, which you would just compute this way, you would find that that has some non-zero flux. Okay. Now the important point that Hawking is trying to make is that this flux that you compute, and that's the next, and this is the, in some sense, the quantum version of the classical argument about the causal structure previously. The important point that about this flux is that this flux does not depend on the state of the B omega Ls. And we already discussed this in the previous lectures. Right, there were even questions which said, how, when we derived this formula for the occupancy of these A modes, there were questions about, does this hold in any state? And we said, yes, it holds in any state. And in particular, we even discussed the ambiguity. You could think of different kinds of states, the Unruh state, the Kruskal state, where you put the B modes in different kinds of states. And the important point is that this flux that you get at Scri plus, does not depend on what the B modes. And so it does not have any information about the B modes. And this is the analog of the fact that in the classical theory, you need to specify data on the horizon, and then you need to specify data on Scri plus. And these are independent pieces of data. These B modes you can think of as specifying data on the horizon, and these A modes are specifying data on Scri plus. And what Hawking is finding is that you're doing a computation for the state of the A modes as formed from collapse, and this computation doesn't depend on the B modes. It doesn't have information about the B modes, and that's consistent with the classical causal structure of the space-time being different from the structure of Minkowski space. Okay? So this is an important observation. This is the first observation. Second, one can not only does it not depend on the B modes, you can actually compute the state. Okay? So one can compute not just the correlators, one can compute the state of the A omega L modes. Okay. And the way Hawking computes this state is first, if you look at this paper, Hawking is doing this computation of these occupancies, and then there's some computation which once again you can look at. But in the end, this answer that Hawking finds is the same answer that we have, except that notice that in Hawking's computation, if you try and go through this paper, Hawking includes the gray body factors in his computation, which we have dropped because we have defined these small A modes, which you should think of in some sense as modes near the horizon. And so these small A modes don't have these factors of T omega. and these factors of t. So, but apart from the factors of t omega, you can compute the 2-point function of these modes. But not only can you compute the 2-point function of the modes, you can also compute higher point functions of the modes. Okay? So we already computed the expectation value of n omega. There's actually something I should plead guilty to, which is that I'm actually fond often of writing a omega dagger. That's by putting the a omega on the left and the a omega dagger on the right. The number operator is actually ordered the other way, so please don't get confused. I will try and be careful. So the expression I wrote down previously was correct, but it's also correct that n omega is 1 by e to the beta omega minus 1. It's not 1 by 1 minus e to the minus beta omega, because there's a factor of plus 1 between these two. And when I write n omega, just remember it's this ordering. And I just happen to be, for some reason, fond of the other ordering, so I often write the other ordering as well. So just, if you're doing the notes, just remember to be careful and not get confused by this. So this we already computed. In fact, this follows from just taking the previous answer I wrote and adding one or subtracting 1 from it. But Hawking, you can also compute what n omega squared is. Okay, I'll just write down the answer, and then I can explain to you why this answer, how you'd work out this answer. One way to work out the answer would be to go back, to position space and write down the fields, and then do the Fourier transform. We derive this n omega in the end by looking at some correlator in position space and then transforming it to look at these modes. But there's a simpler way to derive an answer of this kind. This, in fact, is the analog of what you will see Hawking derives when Hawking works out n omega squared. But the simple way to understand why this answer and other answers, have to work out in a certain way, is to focus on the fact that not only did we work out the occupancy of these a omegas, not only when we did this analysis did we work this out, but I spent some time trying to emphasize that any smooth state of the theory obeys a certain equation in terms of these a modes and these a tilde modes. So in particular, remember, maybe I should go to the next page. We introduced these a tilde omega L modes, and we said that these a tilde omega L modes and these a modes obey this kind of an equation. So if you have the black hole is some state in some quantum theory, and the state obeys an equation, a relation between these a tilde modes and these a modes. And let's say you focus only on the state of these a's and a tildes. Okay? So a's and a tildes are some simple harmonic degrees of freedom. There is a quantum field, there might be quantum fields, maybe there are strings, and there are all sorts of other complicated degrees of freedom in the theory. But let's say one chooses to focus only on these two simple harmonic oscillators. Okay? One focuses only on the state of these two simple harmonic oscillators and not on the state of the system otherwise. Then you can solve this equation, and you will find that the state of the system, the state that satisfies this kind of an equation is this state. Acting on the state n omega equal to 0 and n tilde omega equal to 0. Okay? So if you start with the vacuum of these simple harmonic oscillators, then because these simple harmonic oscillators are entangled with each other in a particular way, because they obey a certain relation, you can determine what the state of these two simple harmonic oscillators is, forgetting about what the state of the rest of the system is. Once you have determined the state in terms of these a's and a tildes, remember the a tildes were some observables that were behind the horizon. Right? Now, but for the asymptotic observer, for the person who's living at Scri plus, you don't have information about the a tildes. So for the person who's living at Scri plus, if that person is just computing correlators of the a's or the a daggers, then that person will find that correlators of any polynomial of this n omega, remember this n omega is just a dagger a, the correlators of any such polynomial can be worked out by just doing something like this. Can be worked out just by writing down a simple density matrix for this object, where this density matrix is just a thermal density matrix. Okay? Minus beta also. Okay. And this just comes by taking the state I have here. I wrote down a state for the A's and the A tildes, but in addition, I could now forget about the A tildes, right? So to get this state, I focused on the A's and the A tildes and forgot about the other states in the theory. But now I could say, I'm an asymptotic observer and I only want to focus on the A's and what you see from the A's and polynomials of the n omegas. And if you did that, you would find that every polynomial of the n omegas you could derive by using this thermal density matrix. This is a simple computation, and it's kind of obvious from the fact when you look at this. Right? When you look at this, and if you just look at what the state of the A's is, you will see that that state has to be a thermal state. Okay? It's also true, by the way, that if you were to compute polynomials of n omega 1 times n omega 2, they don't have any correlation. Okay? And therefore, the entire density matrix of the radiation at infinity looks like it's given just by a product of density matrices for each such mode. And so it looks like the entire state at null infinity is a thermal state. Okay? So this is the point that Hawking wants to make here. That one can evaluate the second term. So this is Hawking's computation of the second term. Once again, there are these gray body factors and so on that appear in Hawking's computation. But then Hawking says that one could compute arbitrary powers, right? One can compute higher moments.
Question.
Proceeding, just give me a second, I'll come. So proceeding inductively, you can compute higher moments. And when you computed higher moments, you would find a probability distribution. This probability distribution is just a thermal probability distribution. So you see here, right? This is just a thermal probability distribution with the gray body factor, which we've not included. But apart from that, we have not included because we are looking at slightly different quantity. Apart from that, this is just a thermal distribution. And this is what I just explained. Okay? So this is Hawking's second point, which is that, using the computation that Hawking did, Hawking claims that you can in fact compute the state at null infinity, and that state is the thermal state, as Hawking says. I told you, because I did the calculation and I now found that the state is the thermal state. Okay, there were some questions, so maybe I can take a question here.
Yeah. So is the vacuum defined usually? By it annihilates by both A and A tilde?
So this vacuum here is indeed defined that way. So this is a special vacuum. This is a vacuum which is annihilated by, in this Hilbert space of the theory, you can always start with any state and keep acting on it with A's till you end up with a state which has n equal to 0 and n tilde equal to 0. And that state is indeed annihilated by A and A tilde. We're not saying anything about the global vacuum of the theory, but this is indeed the vacuum for these two simple harmonic oscillators.
Okay. Yeah.
Right. Suvrat, there's a question in the chat.
Yeah, sure.
He's asking if that factor is really e power. Like, is there a double exponential or a single?
Yeah, there's a double exponential. Yeah,
okay.
It's e to the power minus beta omega by 2. Yeah, okay. There's a double exponential.
Right. And one more question is, why does the state psi look like a pure state?
It does look, so, if you focus on these A's and A tildes, it does look like a pure state. I mean, that's one of the nice things of what we derived previously. It's the fact that A's and A tildes are kind of, maximally entangled with each other. So when you have something that obeys a relation of this kind, you can solve it. And, it's, if you just focus on the A's and the A tildes, these things are entangled with each other. And so it looks like a pure state. So it looks like, you have these clumps of pure states, which are, all in A's and A tildes of each frequency are entangled with each other. And and that's the reason you're getting this density matrix for the A's, a product of density matrices, where the different omegas are not entangled with each other, but each A is entangled with its A tilde partner. Okay.
Okay. Yeah, that's it.
Okay, great. Excellent. So very good. So we found, okay, so now the important part, the important part of the final state that we computed on Scri Plus is that the important part of the final state that we computed on Scri Plus is that this is not a pure state. Okay? So if you compute the state of all the modes A omega L's, which specifies the state at Scri Plus, not just of this one mode that we computed, but of all the modes, you will find that that state is also just obtained by taking these rho omega L's and multiplying them together, right? And this is not a pure state. Okay? And so we find that whatever state we start with, we have on Scri minus, we end up with a thermal state. With a thermal, and this is a thermal state on Scri plus. Okay. And this is obviously a paradox because it's in contradiction with unitary evolution of quantum mechanics. Okay, let me just make this extremely explicit because sometimes I find it's not completely clear. So let me just make this very explicit. You know, quantum mechanical evolution takes a pure state, and multiplies it with a unitary operator. So we have a Schrodinger equation. There's a time evolution operator. The time evolution operator has to be a unitary operator. So if you start with some initial density matrix, let's say this is an initial density matrix, this thing, then after some time evolution, it goes to a density matrix of this kind. So this is a pure density matrix. Then this is a pure density matrix. Okay, so this is also pure. So the idea that a pure state could go to a mixed state, which is what Hawking is saying he finds, Hawking says, I'm doing the computation on Scri plus, I'm finding explicitly the occupancy of all these modes. You see that it's a mixed state, you can compute, you can do this calculation, it's a mixed state. And this is clearly inconsistent with the unitarity of time evolution. Okay? Now, the fact that a pure state has evolved to a mixed state is a sign of the fact that one has lost information somewhere along the way. Okay? Now, the reason it's a sign of the fact that one has lost information somewhere along the way is because you can always think of a mixed state as arising by starting with a pure state in a large system and by throwing away some information. If you think of a mixed state that way, the fact that you started with a pure state on Scri minus, which had all information about the system, there was a wave function which had all information about the system. You did this time evolution, you formed a black hole, and Hawking did the computation of the emission of particles from the black hole. And the fact that you find a mixed state at Scri plus is a sign of the fact that you have somewhere lost information. And it's by losing that information that you're finding this mixed state. Okay? So Hawking, in fact, gives some intuition for why he expects that this answer is not surprising. Okay? So he explains why it is that you should expect that you get a mixed state. By the way, let me just emphasize, this is already a paradox. Okay? So this is, you can, the pure state evolved to a mixed state. So one can say that this already is Hawking's original statement of the paradox. We'll have a little bit more to say about the argument and the intuition that Hawking gives for why this paradox arises. But I just want to emphasize that this calculation has already led us to a paradox because we seem to have found that whatever state you started with on Scri minus evolved to a mixed state, and that's a problem. Okay. Now,
sorry, can I ask you a question?
Someone a question, yeah.
Yeah. So even classically, you are saying that the final state, I mean, when you talk about the final state in this background, we needed to consider both the horizon and Scri plus, right? So, but now we are calculating the state at only Scri plus.
Yeah.
So isn't this obvious that it should be a mixed state because we are not even looking at the full.
Yeah, good. But you see, the point is that I'll draw the Penrose diagram a little bit later. But this Penrose diagram I drew earlier. This Penrose diagram I drew here. This Penrose diagram is clearly the Penrose diagram which doesn't take into account back reaction. Because you have a black hole which is formed and it's not evaporating. We will draw a Penrose diagram a little bit later. But if the black hole evaporates away entirely in the end, then once again you have Scri plus. So right. You should have information should come out on Scri plus. So the question is, what happened to the information on edge? So what Hawking is saying is, I'll draw the Penrose diagram in maybe 5 minutes. But what Hawking is saying is, we did this computation. We found this in the classical system when the black hole wasn't evaporating. It already looked like there was a problem. But now I did this quantum mechanical computation of the state on Scri plus. The state on Scri plus looks like it's a mixed state. And in the end, the black hole is gone. So that's what we said in the beginning about the black hole not being there. So there's no more data there at the horizon, right? So this data at the horizon is kind of lost. And that is indeed the next point that he wants to make. And that's the reason you expect or he expects to see a mixed state.
And just to be clear, so these correlation functions that you have calculated,
yes,
we were assuming that the black hole has not evaporated, right? So we were assuming that the black hole is there.
You're right, that the correlation functions that we computed were computed in an approximation where we assumed that the black hole was not evaporating, and there would be a correction that would come from the fact that the geometry actually does not exactly have a late time isometry. But as I said, the assumption is that you have a quasi-static system, and therefore these correlation functions are still accurate at a good enough level. Indeed, that's one of the questions one can ask about this thing about this computation, which is one computed some correlation functions without taking into account back reaction, and then one is adding in back reaction, but one is not computing the correlation function self-consistently in the presence of back reaction. So one could ask this kind of a question, and indeed, this is how we have done the computation. That we did the computation in a static geometry, and now so we're kind of trying to mix and match two things. We're saying, well, we do the computation, we get the flux causes the geometry to back react, but we didn't really do the computation, the full back reacted geometry, which is a fair criticism. Okay.
Actually, there's one more question in the chat. He's asking, is it right to say psi is a bunch of Bell pairs of ingoing and outgoing modes?
No, this state, well, so this psi, no, actually, I should have written something here. Yeah, thank you for the question. Actually, I should have been more clear here. Times other degrees of freedom. So this state, you're right, actually. Thank you. I should have been more clear. This state psi is the state I wrote when I'm focusing only on the A's and the A tildes. Okay. So indeed, psi could have other degree. There are other state there, other degrees of freedom which I haven't focused on at all. So it could be that the A's don't give you the complete description, and there are other degrees of freedom which I haven't written down. But by solving this equation, this is all we got. We found that this is all we got. Now it is indeed the case that if you focus, the A's are supposed to give you a full description of the state in Scri plus, and therefore if you focus on them, you get a rho omega L by just tracing out the A tildes. Okay. But in this equation where I solved it, I should have written down the fact that there were other degrees of freedom whose state is not specified by this equation on top.
I have a question.
Yeah.
Once the black hole starts evaporating, don't the A tilde modes also become accessible at Scri plus?
Yeah. So this is a question where the A tilde modes come out in some sense. Yeah, but the point that we want to do is in the end compute what the rho omega is. We only wrote the A tilde modes as a shortcut to computing what the rho omega L's were. Okay, so we can discuss a little bit whether something becomes accessible or not. Maybe if you give me a few minutes, we can come to this question of whether things become accessible or not. I'll say a little bit more about that. Yeah, you're right. You could ask this question. Could it be that some information from behind the horizon leaks out or something else happens? At this point, I only wrote down the A tilde modes as a shortcut for computing what the correlators for n omega L to the power q were. Now the point is that if this correlation function is accurate, then this is the at infinity, in the end you're only going to see these A omega modes. You're only going to see the outgoing modes, right? So when you say the A tilde modes become accessible, what you must be meaning is that in some sense this n omega L gets modified. Because the A tilde modes are not going to come out in any sense. The infinity modes at infinity are going to be the modes that go like e to the I omega u at Scri plus. Okay. So it could be that maybe these correlators get modified in some way, and we will in fact discuss that. But for now, the assumption is that this correlation function computation that we did is accurate enough, and it seems to be suggesting there's a thermal density matrix. Okay. So Hawking gives some. I mean, so I'm sure when Hawking did the first computation, all these questions could have been asked, right? You could have asked exactly all of these questions, and somebody could have said, you did this computation, but there are all these other effects that you weren't so careful about, and so why do you even expect, or why is it consistent the fact that you got this mixed state? And indeed, the intuition for why you should trust this computation indeed comes once more by looking at the Penrose diagram and by taking seriously the causal structure of the space-time. Okay? So in fact, that intuition is in the beginning, although we skipped over it, but we'll come back to it. So the intuition, the reason that Hawking trusts his computation is that Hawking states that if you look at the causal structure of the black hole space-time, there is a region behind the horizon which forms a hidden surface. And because you have this hidden surface, and because you take the causal structure of the space-time seriously, you say that you have a Penrose diagram, and you can't, at Scri plus, this hidden surface doesn't communicate with what's happening at Scri plus. Therefore, one should adopt a principle of ignorance for this hidden surface. Okay, so this term principle of ignorance that you see here makes its appearance multiple times in the paper. And Hawking says that you have this hidden surface, which is basically the region behind the horizon. This hidden surface, you have to adopt a principle of ignorance, and you should sum over all possible configurations of the hidden surface that are consistent with what you can see outside. And Hawking's point is that all you can see outside is the mass, the angular momentum, and maybe the charge. And it's true, as people were just describing, that these things are changing, but that's a one parameter change. And in the end, that doesn't, Hawking says, doesn't give you much information about what's happening on this hidden surface. And therefore, to compute the state on Scri plus, you should sum over all configurations of the hidden surface. And then Hawking goes on to show here that indeed this will lead you to expect a mixed state. And that's why the computation of this thermal mixed state that we are getting at infinity is reasonable. Okay? So let me just explain what Hawking's point here is. So that's the point here that you see here. I'm rather than reading the paper, I'll just try and explain independently what Hawking's point is. So Hawking's point is that let's say you represent the state on I minus, as some vector in some Hilbert space H1. Okay, so let's call this psi minus A, and this belongs to H1. Okay, this is some vector in the Hilbert space H1. Then, as we discussed, there is a Hilbert space which is a Hilbert space in the future, and that Hilbert space is this is once again going back to the intuition that one got by looking at the Penrose diagram, is a direct product of a Hilbert space that lives at the horizon and that lives at Scri plus. Or if you were to take a Cauchy slice, it's a direct product of the degrees of freedom that are behind the horizon and the degrees of freedom that are outside the horizon. Okay? So you could define the fact that, by the way, when you read the paper, you will find that there are these indices that appear here. This is just to emphasize that this is a vector. This is a vector. And so, Hawking is just saying that, you have this state which is psi minus. This is a vector, and then it has many indices because there are many, this is a large Hilbert space. And so you have to give me a vector to tell me what the state on the Hilbert space is. And then we have something which we can call psi h, and this belongs to H2. And this we can think of as the state at the horizon, or the interior, or the hidden surface. And then we have some psi plus, and this we can call it, which is part of H3, which is the state on I plus, okay? Which is what Hawking computed. Okay? And Hawking states that, and so there's an assumption, by the way, which we will see here, there's an assumption that there's an assumption of locality. It's the fact that if you take some Cauchy slice, you make it run through the inside of the black hole, you make it run through the outside of the black hole, the degrees of freedom factorize into the degrees of freedom in one part of the Cauchy slice and the degrees of freedom on the other part of the Cauchy slice. And in a local quantum field theory, this is indeed correct. Right? This is indeed how degrees of freedom behave in a local quantum field theory. And this is the assumption that Hawking is making here, that the final state, so this is the initial state, and this is the final state. Okay? This final state can be written as a vector in a direct product of a Hilbert space H2 and a direct product of the Hilbert space H3. And Hawking says that, if you wanted to write down an amplitude, the amplitude to go from some state on Scri minus to some other state on Scri plus is given by basically, some S matrix. And the S matrix has three indices. The reason it has three indices is it has one index for the in state. It has two indices for the out states, because there's one index which lies on the hidden surface and one index which lies on Scri plus. And so an S matrix would be given, an amplitude would be given by something like this. Okay. This is an amplitude to go from psi minus, okay, to psi h times psi plus. Okay, but then Hawking says, if you throw away information about the hidden surface, as the causal structure of the space-time suggests that you should, if you throw away information about the hidden surface, then you can only later compute the probability to get some answer on Scri plus. You can't compute the amplitude. You can't compute the amplitude because you don't know what the state on the hidden surface was. But if you were to assume that the state on the hidden surface, if you were to adopt as what Hawking calls the principle of ignorance, and you were to just sum over all possible states on the hidden surface that are consistent with evolution, then summing over this would give you a probability for what happened on Scri plus. And the probability, the way you would compute it is you sum over all of these states on the hidden surface and you just square the amplitude, right? It's what we are taught to do in quantum mechanics. So you square the amplitude, you write down one more factor, you write some complex conjugates, so it's a long expression, but it's really a very trivial expression, so please don't get intimidated. I've just written down the expression and I wrote down its complex conjugates. My H and my star looks all the same, as does my plus. So that's good because it means you have to work it out carefully on your own, but it is really very simple. But once you do this and you sum then over this psi h, okay, you have to sum over this psi h. And if you sum over the psi h, you will find that, when you sum over a complete set of states, the sum over psi h gives you a delta BB tilde. Okay? That's how it works. If you sum over a complete set of states in the middle, you have two indices, you always get a delta BB tilde. And this is just going to give you SABC, S star A tilde B C tilde. There's a sum over B. And then you'll get star, and then you'll get something which will look like. And this quantity is the density matrix for the final state. Okay? Because you started with some initial state, you're in the end only interested in asking about what is the probability to get some outcome at Scri plus. That part you see here, that's the psi plus. And then you have to sum over the initial state. You also summed over all states on this hidden surface, that's the psi h here. And when you did the sum, you end up with an SS star, and then you sum over all indices of the initial state. And you can see that this is a mixed state. The reason it's a mixed state is because you did this sum over psi h. So this is the final state density matrix. And Hawking gives this intuition actually in the earlier part of the paper, even though we've come to it later, to say that, we are going to expect that in the end, the density matrix we are getting is a mixed density matrix, because the process of computing the state at Scri plus is going to throw away information about this hidden surface. And therefore, it's not surprising when you throw away information about part of a state that you get a mixed density matrix. Okay. So Hawking said, because you did this, you traced out part of the system, you got a mixed state, and therefore one must get not a scattering operator, but what's called a super scattering operator. This super scattering operator is some generalization of belief, or, Hawking wanted to argue it's some generalization of the usual unitary time evolution, which is something that could take pure states to mixed states. Okay. Okay. So this is the essence of the argument that Hawking had. I'm going to say one thing more, but as we already discussed, there is in fact a very nice and convenient diagrammatic way to summarize the entire argument. And the diagrammatic way to summarize the entire argument is to draw a Penrose diagram that now includes back reaction. And that Penrose diagram looks like the following. Okay. So just a second, I'll just, oh, you can't see that. One second. Let me redraw the horizon in a color that all of us can see. Okay. And then one has some infalling matter which formed the black hole in the first place. That's here. Let me shade it. So there's some infalling matter that formed the black hole. There's a horizon which is sitting here. This is the infalling matter. there's a horizon, there's a single, and this is Cry plus. Okay, so this is now an extended part of null infinity, and the reason the diagram looks like this is because of what we discussed earlier. It's the fact that you have a black hole where the surface, the horizon is almost always a null surface. It's not. It's almost always looks like some surface which is some null surface. But then in the end, the black hole evaporates, and when it evaporates, you need to add on some part to the Penrose diagram to capture the later part of the space-time, which is when the black hole has vanished. And this is what Hawking argued that the Penrose diagram would be. Okay, I want to emphasize that this Penrose diagram is not what one might call, this is not like rigorously calculated. As we already discussed, this is not like computed by doing some calculation of the entire back-reacted geometry, but it's kind of argued. It's argued by all of these assumptions that we made and all these arguments about approximations that we made. And one says that one has this computation, and when one includes the back reaction of the flux, this is the causal structure of the space-time that we should get. And from this diagram, if you take causality seriously, the one-line summary of the entire argument is that the information that falls here is destroyed. It's destroyed in the singularity because it doesn't connect. So you have some information here. So let's say you were to draw some information that falls in here. This information gets destroyed in the singularity, and it doesn't connect with what's happening at Cry plus. Okay, so that's the one-line summary of Hawking's original argument. Okay? Once again, I want to emphasize that this is not a very systematic diagram. It's not like a very systematically computed diagram, but it's meant to emphasize that the causal structure of the space-time is very different from the causal structure of the initial of Minkowski's space-time. Okay? Now, there is one more important point that Hawking made, which is when the black hole evaporates here, there's some point here, there is some final burst of radiation that's given out by the black hole. So the black hole becomes very small, and then there's some burst of radiation that comes out, and this burst of radiation, when it comes out, at this point, you don't know if the arguments you're making are valid. We already discussed that in the beginning of this lecture. And so someone could have said, and in fact, some people still do say, that, maybe all the information about the initial state is not destroyed, but somehow it moves from here and comes out to this point. And once it comes out to this point, it then emerges out to Cry plus. So in fact, you do get all the information out because the information just lives in the black hole till it becomes very small. And in the end, when the black hole evaporates away, or whatever is left behind with the black hole, maybe if there's a remnant that's left behind, that remnant carries all the energy. Okay? So Hawking, in fact, did address this issue also in the original paper. And this issue is addressed, let's see if I find it. Yeah, here it is. Okay. So, Hawking addressed this issue of remnants, and this is an important point in the paper, which, is I think, a valid argument, which is that Hawking said that, you might have thought that all the information stays till the end and then comes out, but, information requires energy. Okay? And the reason information requires energy is that, if you think of how information is stored in terms of having some system which has a large number of microstates, and then which microstate it is in gives you information about that. I mean, that's the way information is stored. Classical information is stored on the hard disk because the hard disk has a number of microstates. It always looks the same from outside, but in fact, there's some internal microstates, and those are the ones that store information. That's also how quantum information is stored. Okay? And so information, the fact that you have a large number of microstates requires you to have some amount of energy. Okay? In the theories that we understand and we know well, we always find that to have a large number of microstates requires a large amount of energy. There are some there's some recent developments about flat space and soft hair and so on, which we'll discuss later. But Hawking's point was that information requires energy, and there is just not enough energy that is left in the final stages of the evaporation. Okay? And that is because in the final stages of the evaporation, which is when, quantum gravity effects become important, then, the black hole has already become some Planck scale kind of black hole. Maybe it's 100 times the Planck scale, or maybe it's a string scale black hole, and, all this computation doesn't work in string theory. So maybe it's, it's larger than Planck scale, but it's a very small black hole. But the point is, you could have initially started with an arbitrarily large black hole. And if you started with an arbitrarily large black hole in the beginning, then this arbitrarily large black hole would have had a lot of information to start with. And this information you just cannot store with whatever energy you have in the end, because that energy is just fixed by the point at which the computation breaks down. And that computation breaks down when strong quantum gravity effects become important. And that doesn't depend on the initial mass or the initial energy of the black hole. Okay? So Hawking's point is that to carry the same information that you had initially, you'd require the same number of particles as have been emitted in this quasi-stationary phase, as we discussed, but you don't have so many particles at hand, and therefore you cannot have this much information that's left in the black hole in the end. Okay, so this is the point that remnants are not viable. Okay, so this is the other point that Hawking made. Okay? And they're not viable because information requires energy. Okay, so this is the summary of Hawking's original argument, which we've gone through in some detail. And as I said, I would strongly urge all of you to try and read this paper and try and understand what the argument is. As I said, it's important because many times there is a discussion of Hawking's paradox, but using arguments which are different, and there are many very interesting puzzles about black holes, which is what we'll spend the rest of the course on. But this is Hawking's argument. Okay? So we would like to now examine the viability of this argument. But before I go there, maybe I can pause and see if there are questions, and then we can go forward and examine this argument in more detail.
Hi, so is there a calculation of the length of the singularity up to evaporation?
The length of the singularity. What do you mean by length of the singularity?
As in the length of the from this diagram you have right now. There's a point up to which the horizon meets the singularity, right? So we seem to have said that the information, at least the information which went into the singularity, should be really lost.
Yeah, so I'm not sure what you mean by length of the singularity, but there is a point at which this point I was trying to mark in the end about the final stages of evaporation. I was just saying that there is a point at which the approximation that we are making break down, because in all the approximations that we have made, we have always assumed that m over m Planck is much, much larger than 1, where this is the mass of the black hole, and this is the Planck length. There's the Planck mass. Okay. And a black hole which has m equal to Planck mass has a Planck length horizon. So we have always been assuming this is the case, but eventually as the black hole evaporates away, this ceases to be the case. And so, there could be some point at which the calculation we are doing, this quasi-stationary calculation we are doing, ceases to be correct. Even otherwise, you can see this, we made this assumption even when we computed this 2-point function. We said we are computing a 2-point function over a length scale, which is large compared to the UV length scale, but small compared to the curvature scale. When the curvature scale starts approaching the UV length scale, we don't have this hierarchy where we can do this computation. So if you just go back to the first lectures, we always assumed there was a hierarchy between the UV scale and the curvature scale. That's written in this equation. And if this hierarchy stops being there, then the computation stops being valid. And so maybe, this computation of a thermal spectrum is not valid in the final stages of Hawking evaporation. But Hawking's point is just that when this happens, the mass is the Planck length, but is the Planck mass. But you could have started with a mass that was, the mass of Sagittarius A star, which is much, much bigger. And where is all the, information requires energy. And so the Planck mass just doesn't have enough energy to compute, to contain all the information that was there in Sagittarius A star to start with. I don't know if that answered the question, but yeah. Somebody says, so Monica says, can you elaborate on information requiring energy? Good. Okay, I could elaborate on information requiring energy. The elaboration is as follows. The information you would store in terms of, so, you can store information, one can store in microstates. because you see, classically, if you wanted to store information, the way you would store it is by having some system, and the system can have some number of states, and depending on what state this final, so let's say one said that there was this Planck scale remnant which carried all information. The way that would have to work is that the Planck scale remnant would have to have enough microstates so that depending on what initially fell into the black hole, or what the initial configuration of Sagittarius A star was, this Planck scale remnant has one microstate. If the initial configuration of Sagittarius A star was something else, the Planck scale remnant would have a different microstate. And so information has to be stored in microstates, but we have a count of microstates, right? The number of microstates is e to the s, right? So the fact that information requires energy is the fact that s as a if you just compute s at some energy, that this is bounded. So if this is the case, then then you have to have the only way you can store information is by using these microstates. And if you had if you have a system where the amount of entropy at a given energy is bounded, you can't store more information than that. And it is almost you're almost forced to the fact that the entropy at some given energy has to be bounded, because if the entropy, if you had these particles, if you have some theory in which you have a huge number of particles or a huge number of states of different kinds of microstates living below some energy, you would end up not only having these huge number of microstates, if these particles could actually be produced as some stable particles that could run in Feynman diagrams, you would end up destroying the validity of effective field theory just at ordinary everyday energies. And the reason for that is, let's say you try to scatter like some particles, right? And if you had like a huge number of particles that could run in loops, if you had like intermediate remnants which could run in loop, or sorry, let's say these are like remnant particles. So you could have like virtual remnants being produced and destroyed in loops. This would just spoil like ordinary electron-positron scattering, because these loop effects, this production of these virtual particles would be so large that it would just spoil ordinary effective field theory. And so now, as you know very well, and as some people in this lecture have actually worked on, one could ask questions about soft hair and whether soft hair invalidates this. And this is in fact one of the later papers that Hawking himself wrote and discussed. And so we can come to that later. But in this paper, Hawking pointed out, and it is indeed true of most ordinary theories that we know, that to store some information requires energy. And that is just the fact that the entropy is bounded as a function of energy. And you can't have arbitrarily large entropy for some given energy. I hope that answers the question.
Can I just add, like, is this argument valid even if you assume remnants couple only via gravitational gravitons and so on?
Yeah, I think so, because you could think of graviton scattering. So, the remnants would have to couple to gravity. So if you thought of just graviton scattering, then you would produce the remnants as virtual particles. The formalism of quantum mechanics instructs you to sum over all intermediate states. So in particular, you do have to sum over, if remnants exist, you do have to sum over these remnants as intermediate states. And that just forces you, to sum over all of these states. And if you have so many states, then it's very hard to preserve effective field theory at everyday distances. I mean, maybe you could do something by, I don't know, but I mean, one of the primary objections to his remnant scenario is that is the fact that, effective field theory at everyday distances gets violated. And this was, I mean, anyway, at this point, we're just discussing Hawking's original argument. And Hawking asserted, and I think it's a reasonable assertion, that information requires energy. We can discuss the remnant scenario more, but this is what Hawking's point was, at least. Okay.
Actually, Suvrat, there are more questions in the chat.
Yeah, can I just say a few more things, because we're coming to the end of the time, and then we can take questions. We can have the discussion. So I just want to say a few more things. So there are two questions that we'd like to ask. Okay? So if you think about Hawking's computation, there are two elements of the computation that are really crucial. So one of them is the computation of the thermal density matrix. So the computation of the thermal density, in fact, from a computational point of view, this is kind of the key computation that is done. It's the fact that you do this computation of Hawking radiation and you compute a state which looks like a thermal state. Okay, so this is the key computation. And then there is some intuition that comes from the causal structure of spacetime. So there are these two elements that enter into Hawking's computation. Okay? And we now the main point we would like to make, and that we will explore tomorrow, is the question of is it really the case? Is it really the case that the computation we did implies that the final state is mixed? Okay, so we want to ask, is it really true that this computation shows a mixed state? It looks like it does, right? Because we computed some density matrix and we found that all the correlators we were computing were consistent with a mixed state. But is there really this kind of distinction between a pure state and a mixed state? And sometimes, you might have thought that there is, but we are in fact going to argue that the computation we did does not conclusively show that the state is mixed. And so for that, what we'd like to do tomorrow is explore how close mixed states and pure states can be. And the second question, which in fact we will discuss in less detail tomorrow and day after, but tomorrow and the next lecture, but is a theme which will run throughout several lectures in this course, is whether this intuition about the causal structure, is it valid at the accuracy required? Okay, so I'm going to have to make a lot of these things more precise, but you see, the fact that there's some accuracy which is required is going to come about from our exploration of how close pure states can be to mixed states. And then we have some intuition that's coming from the causal structure. But you could ask, is this intuition really something that you should trust if you require extremely high accuracy in your final computations? And those are the themes that we are going to discuss tomorrow. So let me actually stop the discussion of Hawking's original paradox today. This is actually a good time to stop. We haven't actually said so much that is critical of Hawking's argument, although, as I promised, I think Hawking's original argument one can resolve by asking these two questions that are on the board right now. But so far, what we have done is just go through faithfully what Hawking's argument was, and then we will discuss tomorrow what the possible shortcomings in this argument are. But we can actually stop the formal lecture now, and we can have discussion as we do every time. So I'll stop here and we take more questions.